Welcome, executives and decision makers. So glad you're here for this explainer. Today, we're unpacking a really crucial topic, the definitive blueprint for governing, measuring, and investing in AI-driven intelligent systems. We're going to take some pretty complex engineering concepts and translate them into a clear strategic summary that you can actually use to guide your organization. All right, let's jump right in. I actually want to start by asking you a fundamental question. Think about the legacy applications your enterprise relies on right now. What truly differentiates that static, traditional software from the evolving intelligent systems of the future? Traditional software is kind of static, right? It just does exactly what it was programmed to do, no more, no less. But an intelligent system? Oh, that's a completely different ballgame. My definition, an intelligent system is software that incorporates AI to self-learn and literally improve over time based on data and user interactions. Now, for the C-suite, what does this actually mean? It means continuous value delivery. It's about moving away from rigid, hard-coded programming and really embracing statistical intelligence. These systems learn, they adapt, and honestly, if managed correctly, they become more valuable every single day they're running. Okay, really quickly, here is our roadmap for today. We'll start with foundations of intelligence, move into architecture and practice, explore models and rules, look at the MLOps lifecycle, and finally, tackle governance, metrics, and compliance. Let's go. Part 1. Foundations of Intelligence. Let's look at functional versus non-functional requirements. Notice the clear divide here between functional and non-functional requirements. The functional requirements, things like data processing, reading sensors, consuming APIs, basically, that's just the plumbing. It's what the system actually does. But the non-functional requirements, now that is where true executive governance and risk management happen. We're talking about latency, reliability, model explainability, and absolutely strict adherence to privacy laws like the LGPD. Look, a system can have the most advanced AI in the world, but if it fails on these non-functional requirements, it's not an asset. It becomes a massive liability. All right, Part 2, Architecture in Practice. We're going to ground these concepts using an autonomous car. Let's walk through this scientific blueprint. You can see the logical architecture clearly flowing from data ingestion all the way to a final action. First, data comes in from historical sources and active sensors. Then, it goes through a pre-processing phase, basically where the data gets cleaned up and validated. From there, it hits the core AI models, which are often neural networks, and those pass their output to a decision logic layer, ultimately resulting in a physical or digital action. So let's map that flow directly to our autonomous vehicle case study. Step 1, physical sensors like LiDAR and 360-degree cameras ingest just massive amounts of raw environmental data. Step 2, this data is instantly fed into complex machine learning models that are trained to detect things like obstacles, pedestrians, and lane lines. And finally, Step 3, a decision is made and an action is executed, like slamming on the brakes. And keep in mind, this entire cycle has to happen in literal fractions of a second. Part 3, Models and Rules. Let's dive into the hybrid decision layer. Here's a really crucial point. Intelligent systems rarely, if ever, rely on AI alone. It's almost always a hybrid approach. On one hand, we've got AI models, like neural networks. They're absolutely incredible at complex pattern recognition, like identifying a pedestrian in the rain. But they can also be unpredictable black boxes. So, to balance that out, we have rule engines, based on Boolean logic. These enforce strict, predictable, if-then constraints. Going back to our car example, the neural network identifies the environment, sure, but the rule engine enforces the absolute safety constraint. If the traffic light is red, then stop. This hybrid harmony is exactly how you integrate bleeding-edge AI with strict business and safety rules. Part 4, the MLO's life cycle. This is essentially your engine of automation. Let's see how this all builds over time. A lot of people don't realize this, but AI models degrade. The environment changes, data drifts, things evolve. This timeline lays out the automated MLOps lifecycle. On day 1, you've got batch training on historical data. By week 1, the model is deployed and serving. But the absolutely critical phase is month 1, continuous monitoring for any drops in performance. Because by month 2, the system needs to trigger automated retraining and versioning. For decision makers, you have to understand this. MLOps is not just some trendy IT buzzword. It is the essential operational framework you need to prevent your AI investments from decaying over time. Part 5, Governance, Metrics, and Compliance. Let's talk about performance metrics and protection. Consider this your executive scorecard. Governing an intelligent system means managing the inevitable trade-offs between 3 core metrics: Accuracy is your percentage of correct predictions. Latency is the response time. And throughput is the volume of requests processed. Now, here's the catch. You can't always maximize all three at the same time. For example, increasing a model's accuracy usually requires deeper, more complex neural networks, which, you guessed it, increases latency and slows the whole system down. As an executive, you've got to be the one to dictate that balance based on your specific business use case.
Take this extremely strict metric, for example, less than 100 milliseconds. In our autonomous vehicle case study, or even in smart manufacturing environments, this is the hard service level agreement, the SLA for latency. Think about it. It doesn't matter if the AI is 99.9% accurate. If it takes longer than 100 milliseconds to trigger those breaks, the system fails its functional purpose entirely. It's just too late.
But beyond just performance, there's the issue of trust. As IBM states, and I think they hit the nail on the head here, explainable AI is a set of processes and methods that allows human users to understand and trust the results created by machine learning algorithms. When a system makes a decision that impacts a customer, a patient, or a citizen, you need to be able to explain exactly why it made that decision. Explainability isn't just a nice-to-have anymore. It's absolutely vital for mitigating legal, ethical, and reputational risks, especially in heavily regulated markets. And speaking of regulations, compliance has to be engineered directly into the architecture through privacy by design. This means from the very first sensor, you're actively minimizing personal data collection and using anonymization strategies. It means strict structural adherence to data protection laws like the LGPD. Your architecture has to natively support a user's right to consent, to access, and to immediately delete their data. Let me be blunt. If your data lake and ML models aren't built to easily locate and completely purge a specific user's data upon request, your organization is entirely exposed from a compliance standpoint. Well, we've covered a lot today. The foundations, the logical architectures, balancing models and rules, the MLOps lifecycle, and the absolute necessity of rigorous governance and privacy compliance. So I want to leave you with one final critical thought to discuss with your leadership teams. Is your organization's infrastructure truly ready to govern the continuous lifecycle of an intelligent system? Thank you so much for joining me on this explainer. I really hope this blueprint helps you lead your enterprise confidently into the future of AI.